is actually doing experimental nonlinear dynamics. He'll talk about some of the experiments on probing deprivation plane physics by talking about a supernova in the jar.
Thank you. This is kind of a crazy talk because it's the Coles to Newcastle talk that I'm going to tell you your own business at some point or other. But I'll try not to tell you your own business. In fact, the talk is kind of incomplete. The end of the talk is up to you. Okay? I will tell you what I do, and then it'll be up to you to tell me how it relates to what you do. I think it relates, but maybe it doesn't. It's called, provocatively, a supernova in a jar. And the person who really did this work is my former student, Mike Rogers, who is now a postdoc doing conventional condensed matter physics at McGill University, but he worked on the problem I'm going to describe for his PhD work that he finished last year. We also had some very nice collaborations with some people at Cambridge who helped us with magnetic resonance imaging, which I will come to describe. And numerics were, we used a code that was adapted from one written by Abdul Zabib at Rutgers and Ann DeWitt at the Free University of Brussels. Here's a jar. Here's a supernova in a jar. Done! Really, how do you get the supernova in the jar? Well, really, what this talk is about is a laboratory scale chemohydrodynamic experiment that might, and I stress might, have something to do with the initial stages of a type 1a supernova explosion. And believe me, when we started this experiment, we had no idea that it might have anything to do with supernovas. And so this is a relatively recent idea that these things are connected to each other. And I freely admit that it might have nothing to do with that. And you're going to tell me whether that's true when we get to the end, basically. So this is what the experiment looks like. It's a chemical experiment that takes place in a little vessel in the lab. It takes about 15 minutes to run, and we take movies and we do various kinds of measurements on it. And it is, in some sense, and I will a kind of very gentle exothermic explosion, okay? And it produces a plume-like thing in the jar, and we study the dynamics of that plume. And the question is whether this has anything to do with this lovely astrophysical effect. So I will just tell you about the experiment, and at the end we'll decide amongst, we'll take a vote or something, and we'll try and decide whether there's any connection between the two. First thing you need to know is that chemical reactions occurring in solution can be, they have some kind of kinetics which tells them the rate at which they occur. And if the reaction is trivial, the kinetics are kind of trivial, but it's possible to make reactions with non-trivial kinetics, which are so-called autocatalytic. And what they do is they actually reproduce their own reactants, and this causes a kind of feedback effect. And when you do that, you get nonlinear chemistry, okay? And so the chemical rate equations for this type of reaction incorporate feedback and thus produce quite non-trivial chemical effects. And the reaction that we talked about is a very simple version of this. You can get things like oscillations and so on. But what this does is it produces what's called an autocatalytic front. The reaction is called the iodate arsenous acid reaction, and this is, I'm not a chemist, but this is the reaction. It consists of a slow reaction and a fast reaction. And the slow reaction is basically the oxidation, I guess it is, no, the reduction of iodate. And the other one involves reacting arsenous acid to get, basically change it oxidizes the arsenous acid to O4 state, okay? But the key thing is that this one consumes hydrogen and iodide, and this one produces hydrogen and iodide, and they feed back, okay? So when you put together iodate and arsenous acid together, what happens is we get an orange solution, and it's orange because the pH is low, and we put an indicator in there which just tells you what the pH is. And after the reaction has occurred, the pH is different and it turns blue. But this reaction, this reactant, this orange stuff, is completely stationary and stable until you put in enough hydrogen somewhere to get the reactions going, okay? So it's like a metastable chemical state. If you start a reaction someplace, then reaction takes off, produces its own catalyst, and then keeps going, okay? And that catalyst diffuses to the nearby unreacted solution and sets it off, and that produces the catalyst and sets off the next piece of reaction. So the orange state is completely metastable until you trigger it by lowering the pH somewhere. When you lower the pH, you can trigger it, and this is a simple Petri dish experiment. You put it in the Petri dish, nothing happens, it's completely stable. You put a tiny little drop of acid on the end of a hypodermic needle in the center, and you trigger a kind of front, and that front this way and kind of eats up the orange stuff and turns it blue. And the pH changes so you can see the products are blue and the reactions are pink or orange. And what's happening is that the catalyst, the autocatalyst, is present only at the reaction front. That's the only place it's being produced and consumed. Okay? So it's very much like a flame front. The reason the flame burns is that it preheats the fuel in front of it, and that gets it to burn, and that makes more heat, heats the fuel next to it, and so on. And the thing that's moving in a flame front is the temperature that's diffusing. But here it's the autocatalyst that's diffusing, and there's no catalyst there until you trigger the reaction. Now the key thing about this is it's occurring in a solution, and it changes the density of the solution. But only a very small amount. It turns out that the products are a little bit warmer than the reactant. The reaction is exothermic, so it warms up the product solution by a few degrees. But it turns out it's equally important, it just changes the chemistry of the products. And even at the same temperature, the products are a little bit lighter than the reactant. So there's two effects. It changes the chemistry and it heats it up. And between those two, it produces a density change of about 1 part in 10 to the 4. And the thermal expansion coefficient of water is about 10 to the minus 5. So that's equivalent to something like a 10-degree temperature change of the water. Reality, the temperature change is about 5 degrees, and the other 5 degrees equivalent temperature change is caused by the chemical change. So basically, the blue stuff is lighter than the red stuff by a little tiny bit. Okay, and if there were no gravity, like there is in a very thin sheet of the stuff in a petri dish, then what happens is the front of this thing burns along at a constant speed, which is determined by the chemical rate constants and the diffusion constant of the autocatalyst. So there's a characteristic speed, which is kind of like the flame front speed, which is built into the chemistry. If you do it under gravity, on the other hand, this produces buoyancy effects, and that affects the chemistry, and that's the whole experiment. So without gravity, it's essentially a kind of flame front burning experiment. Now, a long time ago, the chemists were studying these things, and they noticed something weird, which is that when you put it in a thin tube, and you propagate, you detonate the thing, or you set it on one end, it'll slowly burn its way up the tube. And if you put it upward and downward in a very thin tube, the two fronts move along at the same speed. And that's the bare speed of the reaction. So you can measure the bare speed of the reaction by putting it in a capillary tube and just like a thermometer watching it move along at constant speed. If, on the other hand, you put it in a slightly larger tube, then you discover that it goes at a different speed upward as it does downward. And the front gets distorted in the vicinity of the reaction front. And the reason for that is that if the tube is large enough, you set up a convection roll in there because the blue stuff is lighter than the red stuff. And so this thing is light underneath and heavy, and it actually overturn at the reaction front. And that has the effect of accelerating the average speed of the reaction along. And this is kind of stirring it as it goes along. If you make the tube even larger, then you get a kind of donut-shaped mode. So it goes up in the middle and down the outside like this. And people made theories of this by treating the reaction front as a sudden discontinuous density jump that moved along at a prescribed speed, and then you can do the hydrodynamics of this thing. And you find that there's a control parameter that determines the stability of this thing, which is proportional to the cube of the diameter of the tube. And delta rho or rho is the density jump, d is the diffusion constant of the autocatalyst, nu is the kinematic viscosity of water, and g is gravity. And for S less than 88, your tube is stable, and for S around 88, you get this, and between 88 and 370, you get a transition to this donut mode-like thing. You can also suppress the convection by increasing the viscosity of the fluid by adding glycerol. So this is Mike's simple experiment. You measure the front speed as a function of glycerol concentration downward, and you see that it goes down. But it's linear in the concentration of glycerol. As you increase the concentration of glycerol for an upward propagating front, you see it goes down precipitously, and then it joins this one. Okay. So right here, it's no longer convecting, and in here, it's convecting, and the speed of the apparent speed of the front is faster upward than it is downward, and down here it's the same. Okay. So I suppress the convection by making the fluid more viscous. It actually changes the chemistry a little bit so that the front speed isn't independent of the glycerol concentration, but we take that into account. So basically, we can make a fluid whose viscosity we can mess with by adding glycerol, but has this strange nonlinear front propagation built in. So the next most complicated thing you can do is to look at it in a slot. And many years ago, in fact, this is one of the first papers I ever wrote when I joined the University of Toronto. Mike Carey was an undergraduate student in my class at the time. He did this experiment where we made a kind of thin slot, and we propagated it upward, and we triggered it with a little electric pulse. You can trigger it electrically by lowering the pH electrochemically. And now the control parameter is proportional to the cube of the slot thickness. And if you look at the what you get is essentially a flat front that breaks into fingers, and the spacing of the fingers is narrower and narrower as you make the slot thicker. Okay? But then as soon as the fingers appear, they tend to merge together until there's one big finger. So it's a bit like the Rayleigh-Taylor instability. There's no surface tension stabilizing it. The faster the growth rate, in other words, the wider the slot, the bigger S, the smaller the initial instability is, or the bigger the cube of the wave number of the fastest growing mode is. But eventually, it all goes together and produces a finger, which is the width of the slot. So it's a bit like taking a glass of water, turning it upside down, and it's unstable and it runs out rapidly. Okay, but it's important to realize that this is a fluid-fluid interface here. There's no surface tension or anything there. And there's a little bit of diffusion going on there as the heat from the reaction is diffusing ahead of the front and all of that. Okay, but other than that, it's somewhat similar to Rayleigh-Taylor. So many years later, we decided to think about what happens in the high S limit. What happens if you just keep going and go to very large values of this parameter, which controls the stability. So here's an experiment in a tube a few inches in diameter, and it's got water solution just like the one I showed you a minute ago. And we trigger it at the bottom. I don't know if you can see it, but there's a kind of squirmy worm comes up and it wiggles back and forth. And so this is quite unexpected, but it's simple to understand. You have a little plume rising in the center, and it's buoyant, but it's easier for it to go off to one side of the tube and start a convection roll, which is turning like this. And that convection roll drags it to the other side, and then it goes up the other side for a while, and then that starts to roll this way, so it goes back and forth. So the rising plume kind of squirms its way up the tube like this. It eventually develops enough buoyancy that it kind of punches forward and keeps going. So we call that writhing, and then we call this, the last part of the motion, breakaway. Okay? So in the narrow tube, you get a very strong interaction with the sidewalls via this, so there it is writhing, and somewhere about here, it basically begins to punch up center. Okay, now the Reynolds number, depending on, based on the tube diameter here, is a few hundred. So it's not a simple flow. It's not quite turbulent, but it's not simple. Okay, so here's the cartoon that goes with the snake riding in the tube. And what we wanted to do first was to understand how these plumes, and I'm going to call them autocatalytic plumes, differ from the usual kind of buoyant plumes that people know and love. For example, here's a buoyant plume. I call it a political plume. Okay? And if you look at the plume literature, a large number of plumes are geophysical. Most famously, the mantle has plumes which rise from the core mantle boundary and reach all the way to the surface and punch through and produce things like island chains like Hawaii and so on. So most of the plumes that people study seriously are geophysical ones, but also there's a certain amount of study of buoyant turbulent plumes. But there's actually very little study of buoyant or driven laminar plumes. And what we're going to do is we're going to get away from the complexity of the experiment that I just showed you by increasing the viscosity to the point where the flow becomes simple enough for us to understand. Okay, I mean, Reynolds numbers of several hundred are too big, so we back off and make it simple. So the first thing to look at was what happens in an ordinary plume geometry without chemistry. Okay, so and as a kind of control, we looked at the scaling of compositional plumes, that is, plumes which are formed by injecting at a given rate an amount of glycerin water mixture which is slightly more buoyant than the surroundings. And we inject continuously. Okay, so there's two effects. One is that this blue stuff is very slightly lighter than its surroundings, so it's rising due to that buoyancy effect. And also, we're giving it some initial momentum by shoving it out this little pipe using a syringe pump. So there's both buoyancy and momentum flux at the inlet caused by the syringe pump. And we only change, the difference in density is only about 1%. So that gives you a plume which rises fairly gently. And the background fluid, you can change the viscosity, but generally we use something which is much more viscous than water. And that keeps everything very laminar and easy to understand. Now, to our surprise, nobody had already done this experiment. So we did it systematically, and we found some interesting things on it. So I'm going to tell you about it now. So for example, at 80% glycerin, which is extremely viscous, what you get is a rising plume looks like this. Now this is visualized using parallel light beam, which is bent by the density differences in the fluid, and that's called shadow graph technique, just so you know. Okay. If I go to 60% glycerin, then you see, look at the head. You see the head still looks sort of like a mushroom, but it's a much more elongated mushroom than this one is. Okay. On the other hand, if I go to 40% glycerin, which is half the viscosity of this, you see the head doesn't make a nice mushroom anymore. It makes a kind of skirt that hangs down and flaps around and is much more unstable in this case. Okay, so we call these things confined heads. So these are basically have an overturning vortex ring in them, and none of the fluid that comes up the conduit, this thing is called the conduit, escapes the head. Basically, it fills up the head. The head gets bigger and bigger, and it's wrapped up inside the vortex ring. On the other hand, at the opposite limit of viscosity, we found these things which are called dispersed heads, and essentially they fail to close so that the fluid that's coming up the conduit turns around and kind of slops down the sides and produces this, expanding cone of stuff. Okay? The interesting thing about this is that there's this critical state right between the two where the overturning of the vortex ring just fails to close. So there's a kind of a stagnation point here, or a moving stagnation point, which separates the flow. Some of it goes into the vortex ring, and some of it leaks out, and that's the stuff that comes out and makes the dispersed heads. And this happens at a very sharp value of the dimensionless parameters. So in spite of the complexity of the head, it turns out the head, the scaling of the rise velocity, namely the velocity of this point here, is actually universal, and it's very robust for universal in spite of the head shape change. If you write down from dimensional analysis all the things that might be dimensionally important, the two numbers that magically drop out of this are the Richardson number and the Reynolds number, and we write the Reynolds number just in terms of the Reynolds number of the pipe flow that's being injected. So this is the number that you impose basically when you decide how fast you're going to push the fluid into the syringe pump. And it depends on the volumetric flow rate, Q, and the kinematic viscosity of the inside fluid, which is actually the same as the outside fluid, but it's very slightly different than the outside fluid, so we keep it separate like that. D is the diameter of the nozzle. And the other one is proportional to G prime, which is basically G times the density ratio, the difference of density between the inside and the outside of the background density. And this is the Richardson number, and that's the Reynolds number. When you do the experimental remaining Reynolds numbers from all the way from 0.1 to 100, you find there's a beautiful power law scaling. The Richardson number is basically like encodes the rise velocity in it here, and the rise velocity is exactly inversely proportional to the Reynolds number. So a Reynolds number, Richardson number is Reynolds number to the -1 exactly. Okay, and the reason for that is very simple. We assume that the phenomena might depend on the width of the nozzle, the input nozzle. But it turns out that once the thing has grown a few head diameters away from the input nozzle, it no longer cares how big the nozzle, the diameter of the nozzle is anymore. All that matters is the flux of momentum that comes in through that, and the buoyancy flux that comes in through that. And those things are independent of the size of the nozzle once you get far away from the nozzle. And this combination of Reynolds times Richardson exactly causes D to cancel out. And that's the only combination that causes D to cancel out. So in some sense, it can only depend on the product of Richardson and Reynolds numbers, and that makes them exactly inversely proportional to each other. And the nice thing is, for large Reynolds numbers, in other words, pushing hard, you get heads which disperse, in other words, which grow these kind of skirts, and for Reynolds numbers which are very small, in other words, which are mostly rising due to the buoyancy effect, then just as you pass Richardson number equal to 1, the heads become confined. So I can tell you whether you're going to get a confined head or a dispersed head just by checking whether buoyancy dominates over the input momentum or not. But the rise velocity doesn't care about that for all different runs because of this insensitivity to D. They all rise at the same dimensionless, speed, and so the relationship is very power law-like. So, for example, the velocity rise of the head is some dimensionless number, which is not easy to guess, times the only thing you can make out of here, omitting D, which has the dimensions of velocity, which is G prime Q over little one half. Okay, so all plumes are the same as far as a rise velocity goes. The shape of the of the head depends on the ratio of the momentum to the input buoyancy, but other than that, it doesn't depend on anything. Okay, so armed with that information, we can now, and those all rise at constant velocities and their conduits remain cylindrical. Okay, now we can look at what happens with chemical plumes or autocatalytic plumes. So now we decided to try, instead of having the plume rise in a tube of a few inches in diameter, which I showed you before interacted strongly with the walls of the tube, we wanted to do an experiment where we basically released a buoyant plume into an infinite solution where there were no effect of the walls. Now you can't actually do that. All you can do is use a very large tube. So here's a very large tube. It's 32 centimeters tall and about 10 centimeters across. Okay, and it's just bunged with a couple of the largest rubber bungs that you can buy. Okay, and through the lower bung is a little piece of capillary tube, and that capillary tube is stuffed with cotton in order to keep the fluid from moving in there, but it's still filled with the reactable fluid. And this is all filled with unreacted solution, which is red. And then there's a little plug down here, and basically we stick a syringe in there and trigger the reaction at the bottom of this tube. So it's like lighting the fuse, okay? And then the reaction works its way up through the saturated cotton until it gets to the end of the tube, and then it escapes. And ideally, this thing is so large that it doesn't interact with the wall. As we'll see, in fact, the stuff is still viscous enough that it does feel the walls, but it's at least very, very large. Okay, so this is an unconfined reacting fluid released into a cylindrical tank. What happens? Well, this is what happens. If you watch closely, you see that there's a little thread of blue stuff that looks sort of brown in this movie. It comes out, and it begins to rise. And initially, the head is a little bit like a little sphere. It has some overturning in it. Eventually, about here, it grows into the mushroom shape. So this looks like the mushroom heads that we've already had before. And then the mushroom head begins to accelerate, which the other plumes do not do. And then it runs away from its tail, basically. It becomes a free vortex ring, almost free. And the tail, it can no longer keep up, and it grows a new head. Okay? And then that head decides it wants to run away, and it runs away, and it grows a third head. And as I will show you, you go up to 5 heads in this fashion. And eventually you're left with a kind of stationary state where the top of the tank is filled with reacted stuff, and there's a reaction going on all the way up the conduit. The fluid is rising in the conduit and kind of filling the top of the tank. Okay, that's called the box filling mode by people who study fluids. Okay, so somewhere after the movie ends here, this thing will just sit here and pump fluid into the top. And eventually, now it's going to start again, eventually the whole tank slowly fills with black stuff until the reaction is finished. So multiple heads are released. Now this is strange because normally a rising plume either rises at constant velocity because it's constantly being fed by a source, or it slows down because as the plume entrains colder fluid from the surroundings, it loses buoyancy and actually slows down. So more conventional thermal plumes, if you feed them constantly move at constant velocity, or if they just entrain cold fluid, actually slow down. But this one, believe it or not, is entraining fuel, right? So as it mixes more chemistry and it generates more buoyancy, so it actually accelerates. So that's a difference between chemical plumes and non-reacting plumes. So here, this is the famous picture, which is framed from the movie, which actually got onto the cover of Physical Review Letters. You probably don't even know there is a cover picture on Physical Review Letters, because no one ever looks at the paper version anymore. But there is, and it was on there. And so here is the height of the head as a function of time, and you see that at various times in this picture, it accelerates, and eventually this little slowdown is caused by the head banging into the top of the tank, basically. Okay, now what's interesting about this head is it's kind of like a rising bubble. The fluid is coming up and turning over, and it's kind of trapped in this confined head. And that's a bit like the overturning flow in the air inside of a rising bubble. And a long time ago, G.I. Taylor noticed that the tops of such large rising bubbles were hemispheres, quite accurately. So we can actually fit a hemispherical crest to the top of the bubble. And if you look at how that evolves with time, you find that it's basically different below the pinch-off and above the pinch-off. Once it pinches off, the radius starts to go up, and basically that's because it's headed for being a free vortex ring with a big radius when it's taken off. So here's a vortex ring, And so somewhere out, if I had a tall enough tank, I would be releasing an accelerating vortex ring, which would eventually become turbulent and everything, but it's still very laminar. And that would leave behind the tail, which would generate another accelerating vortex ring. So it's a free autocatalytic vortex ring. But the point is we can locate the pinch-off by looking at the shape of the head. So here's a kind of slightly crappy movie, but if you watch here, you can see that this one releases 5 heads. And it turns out that each bubble is approximately the same size and the same, rises at the same velocity as the previous one, just moved up the tank a little bit. So the slopes of all these lines are the speed with which the head rises. And the last one is slightly messed up because it runs into the top of the tank. But the Reynolds number of all of the heads turns out to be about the same. So this is kind of like a burping faucet or something. It launches bubbles over and over again. It turns out that empirically there is a kind of sweet spot in the viscosity for making multiple heads. If I put in very little glycerol so that it's not very viscous, then essentially what happens is the plume rips up to the top of the tank and it doesn't have time to generate a head that it takes off. If I put in lots and lots of glycerol, then it rises so slowly and everything's so sluggish that it barely manages one pinch off. And if somewhere in between there's a kind of happy medium where it will produce multiple pinch-offs. And I can organize myself in terms of the Reynolds number of the head and the Schmidt number. The Schmidt number is a measure of how viscous the solution is, the viscosity divided by the diffusivity of the catalyst. And that actually changed a little bit when I changed the glycerol concentration too. So this is not a trivial thing. It's not just proportional to the amount of glycerin. And there's a kind of middling Schmidt number at which the multiple pinch-offs are most likely to occur. Okay, we got an invitation to go to do some fancy velocimetric measurements at Cambridge using an MRI imaging machine. It turns out you can basically make a velocity image of the cross-section of the tank as the plume rises through it, and we can look at the velocity structure of the conduit here. And this was done in collaboration with the MRRC at Cambridge, and these guys are sort of the experts at magnetic resonance. So here's a little movie showing the plume coming through this plane. The red is large velocity. So there's the head coming through, and after the head comes through, you can see the conduit velocity, and it's a little messy. And this sort of blinking back and forth is the return flow. So as the fluid rises, some large return flow has to come down again. And so a little bit of is returning down around the outside. And what we find that's interesting is on average, the conduit, when it's fully developed, actually has a low spot in the middle. So a non-chemical plume has a Gaussian distribution of velocity across the conduit. It rises the fastest in the middle and the lowest around the outside. But an autocatalytic plume, far from the inlet, actually has a minimum in the center. So eventually the buoyancy is being generated on the surface of the conduit, and it's pushing it up, and the middle is being dragged along by the rising outside edge. And that actually makes sense, because when you look at the conduits, for a compositional plume, you get a very cylindrical looking thing, but if you look at the autocatalytic plume, it's actually a slight cone-shaped thing, so it's getting bigger and bigger as it rises. And this is simply because the reaction is continuing to make more rising fluid, make more red stuff, turn into the blue stuff, as the conduit is rising. So the angle that the autocatalytic plume makes is quite small, 100 degrees, but it's basically the cosine of the, it's basically the arctangent of the ratio of the upward flow velocity to the velocity of the front. So as the fluid is rising up, it's also expanding, in chemical front fashion, and that's causing the conduit to become conical as it rises. And since this velocity is quite small compared to the rise velocity, it's not a very sharp cone. Okay, so now let me tell you about the numerical model that we made. We used a code that was given to us by Abdel Zabib, who at the time was actually something like the Dean of Engineering of Rutgers. And he gave us an old code that he wrote a long time ago for looking at pre-mixed flames and things like this, and basically an axisymmetric calculation using 1970s Fortran technology, basically. But algorithmically, I don't want to discuss it because it's a really embarrassingly old-fashioned type of code, but what we actually calculate is the following equations. This is Navier-Stokes equation with some driving terms. And then there's two things that are diffusing. One is the concentration of the chemistry, and the other one is the temperature. And they're coupled through this reaction term, and the fluid is incompressible. Okay. So here's what the geometry looks like. It's in R and Z, and it's wrapped around in theta. We use rigid boundary conditions all around, so that it's like a closed cylinder, and various types of initial conditions, which I'll describe. The ratios of the kinematic viscosity to the diffusivity and the thermal diffusivity to the diffusivity of the chemistry are both very large, so the Schmidt number is 9,000, so this is a very small term. And what's called the Lewis number is the diffusivity of heat divided by the diffusivity of chemistry, and it's also very large. The ratio of these two things is the Prandtl number, and so the Prandtl number is also very large. So what this basically means is that the stuff is really dominated by viscosity. And the Schmidt number and the Lewis number appear in the equations here. And we use the Boussinesq approximation, so the density change is linear in the temperature and linear in the concentration of chemistry. The length scale in the problem turns out to be approximately the thickness of the reacting front. So D is the diffusivity, tau is the reaction time constant for the chemistry, and that gives you a length which is very tiny. In the experiment, it's only about 50 microns or something like that. So we have a 10 centimeter size thing, and inside of it is a front, it's only 50 microns length scale, so it's very sharp. And unfortunately, that forces you to use a very large domain, so that the code very naively does not try to track the front. It just grids the whole thing so that it can resolve the front. And so this is turns out to be a very large domain. And it also means that the driving terms, there's both the thermal and the compositional Rayleigh number, they're proportional to the cube of this rather small length. So they're quite small, but they're putting in the values that we know from what the chemists tell us. They're both around one's about 0.2 and the other one's about 0.1. So the concentration is about twice as effective at producing flow as the temperature is, but they're sort of comparable to each other. So this might not look like it's very strongly driven, but that's because the Rayleigh number has been based on this very small length. If you base it on the diameter of the tube, then it's enormous. Okay, so the thing is really far from being stable. But the bottom line is that there's an extremely short length scale in here, which is the length scale of the front, and the diffusion of the heat smears the heat out much larger than that, and the viscosity basically smears out the fluid flow all the way out to the edges of the tank. Okay, so as a one more thing I need to say, and then the autocatalytic nature of the reaction is encoded in this reaction term, which is cubic in the concentration. That turns out to be important. And this comes straight from the way the chemists understand the rate constants of that particular autocatalytic reaction. Okay, so to validate the code, what we did was we just ran it in small tubes, and because it's axisymmetric, it cannot get the single vortex mode, but it can get the donut mode all right. And so we can basically check that we get the same critical value of that number S, and we can do runs in small tubes, and it all works nicely. And then we went ahead and did it in a very large thing. So this is a domain which is 2,000 Li and 500 across. And what I'm going to show you is what happens if we hold the concentration at a little disk at the center of the bottom equal to 1. And that basically is a kind of steady input of catalyst. And then basically the plume is going to develop from there. I should say this was parallelized by slicing it into vertical slices. And the whole thing was run on SharkNet for a long time. And it's kind of a gross waste of computer power, but we resolved zeros up here to fine precision. All right, so what you see is a plume rises. You actually do get pinch off and a free vortex ring. Unfortunately, the domain's a little small, so they kind of pile up to the top at the end. This is the concentration, and it's going to run again. And this is the temperature, so you can see the temperature is kind of smoother than the concentration. And over here is the vorticity, and basically you get a vortex ring in in the head, but actually the fluid velocity reaches a little bit all the way out to the sides of the tank, whichever did better. Okay, so somewhere in there it reached off ahead and ran away, like I described before. Okay, so here's the three fields just for. All right, so it's not quantitatively identical to the experiment for a number of reasons. One is that the tank the actual experimental tank is something like 6 times the size of the, in dimensionless terms, the size of the calculation. And the other problem is that the initial conditions are not simple in the experiment. There's a little pipe and it comes out, and there's exchange flow and stuff happens at the inset of the experiment, which is not reproduced in the calculation. But qualitatively, you get the same result. The plumes accelerate upward, and the head width goes through distinct stages of morphology, and they roughly rise linearly at different speeds, and we see more or less the same sort of thing in the simulation. Although we really typically run at a height in the simulation before we get the fully developed business going on. One interesting thing is a cubic autocatalytic reaction has an interesting characteristic, and that is that as long as it's propagating in a narrow tube, it will continue to propagate. But if you release that same reaction into an unconfined volume, you effectively start a little flame ball, which is smaller than a certain critical size, and it can die, okay? So we found out the hard way that if this tube down here is too small, then the reaction will eat its way up here and release a kind of little wisp, and that little wisp will be insufficient to trigger a plume, and the whole thing will drop dead, okay? And you can reproduce this in the simulation by starting a spherical flame front. I'm calling it a flame, okay? It's not a flame, it's a chemical reaction which is analogous to a flame. If you start a radius here which is small, so this is a radius of only 2L, and then you say go, what happens is the diffusion carries away the heat so fast that they can cross, okay? And so basically, this is a feature of the cubic catalysis that it can actually has a finite radius before it will take off. If I use a very slightly larger one, a 3L flame ball, then what happens is it almost croaks, okay? But then, whoa, it gets away and takes off again, okay? And so look at it, it drops all the way down and then whoops, takes off again. And then it will, so this happens so fast that this has got buoyancy in it, this calculation, but this happens so fast that the ball has not risen significantly during those times. Okay, so we realized that this wasn't exactly what we wanted to do. What we wanted to do was trigger the reaction at a point which wasn't on the boundary. So in the previous simulations I showed you, I held the concentration of the product equal to 1 on a little disk on the boundary, and that's kind of like keeping the fire going there, okay? So what we actually wanted to do was start a very small flame ball which was disconnected from anything. So here's a little tiny flame ball, you can't really see it, but S is equal to 1 in a little tiny disk right at the bottom here. And this is all zeros, okay? And now we're just going to release it, and it's going to be large enough not to die, but it's still very small, okay? And so this is what it will do. It begins to grow, it's spherical for a while, but then it begins to be distorted by fluid mechanics. And then it starts to drag out this great big tail, and eventually the head runs away from the tail, as it did before, and the tail grows a new head. But look, down here, it's disconnected from the boundary, right? There's nothing being put in down there. Okay, now this is interesting for several reasons. First of all, this is something that the microgravity flame people call a flame string. There are these famous experiments where people tried to make Zeldovich flame balls in pre-mixed gases in the Vomit Comet aircraft, which is diving to produce zero gravity, and they trigger the thing and they get a little flame ball, but it goes ripping across the experiment and leaves behind a string. And these are called flame strings, and there's a large literature on flame strings and whether they're stable and all of that. But basically what a flame string is a flame ball which has been rising under its own buoyancy and pulling out a kind of string of flame behind it. So these things I claim are sort of the chemical analogs of flame strings. If, on the other hand, I start with a relatively large flame ball, and this one is way over the minimum size to be happy to continue to propagate, and you see I've already got a lot of heat produced here, you'll see that it rises faster and it stays spherical longer, and it does not drag out a tail, okay? And so this one, there's a little tiny bit of reaction sort of dying out behind it. It's basically not a plume anymore, but a thermal. And a thermal is an isolated region of buoyancy. And so this is, you can think of as evolves into a free autocatalytic vortex ring without the difficulty of having dragged out a flame string behind it. Okay, and of course, it actually stirs the whole tank. It's not obvious, but there's actually vorticity everywhere. Okay, so the story so far is I showed you laminar conventional plumes, not chemically driven. There's a nice transition between buoyancy-driven and momentum-driven plumes where the head shape changes, but we can understand, nevertheless, the parallel relationship between the rise velocity and the Reynolds number driving them. That remains even though the heads change their morphology from confined to dispersed. And believe it or not, although anybody for the last 100 years could have done that experiment, but nobody did. And this terminology actually we had to invent because nobody had a terminology for these kind of heads and all that. Under autocatalytic plumes, I showed you that multiple pinch-offs can occur. And I didn't show you this, but there you can measure the axial velocity in the conduit, and there's interesting schools going on there. And the simulation results reasonably reproduce the experimental behavior, and we see flame balls and flame strings depending on how we trigger the thing. Now the burning question, of course, is what does this have to do with a supernova? Well, my answer to this question is a movie that I'm sure you've all seen a million times, and I've seen it a million times too. It's from the Flash group, University of Chicago, and it shows that the initial stages of the deflagration of the Type 1a supernova under certain assumptions. And they start with a small spherical flame close but not exactly at the center of the star. And what you see is it quickly develops into a rising plume. The plume punches out the far side of the star. For some reason, the star rotates at that point. But the key thing is that it does leave a tail behind it, okay? Now, I'm not sure I believe the sort of cross-shaped morphology of this tail, but it's a little suspicious. But at least you can see that then the star shrinks unaccountably. And what happens then, of course, is that it keeps going. This is a three-dimensional calculation. Now, if you look here, you see the conduit has expanded to a cone, but it's still connected to where the initial thing was started. And eventually, even though the whole thing, people say this looks like a face, that's all the comments on YouTube are about. Eventually, it wraps around to the South Pole. So you see there's a cone-shaped, rather turbulent-looking conduit in there. Eventually, it wraps around to the South Pole of the star. And I guess they think it detonates at that point. Right now, it's all deflagration. I don't really understand the transition between deflagration and detonation. I don't want to express any opinions on it. But basically, the argument is that there's a kind of crunch when it hits the other side, and that produces enough pressure and temperature to cause a detonation wave, and then the star disrupts very quickly after that. So this is a relatively slow process of deflagration. Okay, so what does this all have to do with supernovas? Well, we didn't know it had anything to do with supernovas. I'd never seen that movie until we noticed that somebody, namely Vladimirova, what's her name? Natalia, I guess. She wrote a paper on the initial stages of the Flameball, looking at how it's scaled and how if you change some assumptions about the dimensionless numbers. And she cited one of our previous papers. So we sort of discovered by backward looking at who's citing our papers that supernovas were a potential application. And so the joke is that, so her simulations actually use exactly the same code, not exactly the same code, exactly the same mathematics as what I just showed you, with everything the same, except that she identifies the chemistry and the temperature, so only has one variable and one dimensionless number, not a Schmidt number and a Lewis number, but a single Prandtl number. And a slightly different assumption about the kinetics of the flame, but otherwise exactly the same calculation in the same regime. And produces, flame bubbles that rise and overturn and become propagated like this. Exactly the same. So we wrote a paper in which we discussed our experiments, and then we said a similar dynamic occurs in Type 1a supernova, reference Vladimirova, and unlike supernovas, our experiments are readily accessible in the laboratory. And within 3 hours of uploading that to the archive site, I was getting press calls, okay? For 15 minutes, or about 15 days actually, I fielded dozens of press calls about the supernova in a jar. And I never used the word supernova in a jar in the paper. Supernova was not mentioned in the title or the abstract. It was on line, 27 in the paper. But some science reporter picked it up and wrote a story called Supernova in the Jar, and after that it escaped and became critical. And it was picked up by New Scientist, Discovery News, PhysRev Focus eventually wrote something on it, CBC, National Geographic. And so I've adopted the supernova in a jar, but I didn't think of it, okay? It was somebody else's idea. Here's, for example, the web page from the CBC. Physicists have created a lab chemical reaction mimics the process triggered when a star explodes. So now I see why you guys are so popular, right? Anything to do with exploding stars is vastly more interesting than stuff might happen in a jar. But anyway, so that was quoted fairly accurately, although some of the stars were pretty stupid. But anyway. So now we reach the crucial slide in which we ask a number of unanswered questions, and I hope you can answer them for me, which is really, this has really had to do with supernovas. So here's the wild type supernova, the actual thing, okay? And here's the jar type, or the laboratory, garden variety, or whatever. The wild type has, I hate to tell you this, but I'm around certain parameters compared to everybody here. I can tell you everything you want to know. Every parameter of the experiment is known to less than 10%. I know the densities, I know the chemical reaction rate constants, and I can change them. I can do anything you like with them, okay? That is going to be better than, what's going on inside the collapsed star millions of light years from here, which we don't have any idea what it's doing. I assume you know some of the parameters, but I claim to know them better than you do. Sadly, the actual supernova is incredibly turbulent, whereas my experiment is extremely laminar. In fact, it's not quite Stokes flow, but its Reynolds number is less than 10. So the rise Reynolds number of the, if you think of the head as a bubble or something, it's rising with Reynolds number maybe about 10. Okay, so it's very gentle. It takes 10 minutes for it to rise. That movie I showed you, by the way, to speed it up, it takes 10 whole minutes for it to rise. So it's very, very gentle. I gather from reading some of the literature that it's believed that the Prandtl number effectively of these things is extremely low, which is just to say that the fluid is extremely, almost not viscous at all, whereas our fluid is, the viscosity tends to dominate. So the Lewis and Schmidt numbers, which are the dimensionless numbers which mimic the Prandtl number, are both very large. Obviously, we also have compositional and thermal effects, which are diffusing separately, whereas at least Vladimir Ova's calculation just has thermal effects in it and doesn't have concentration as well. You have a variable gravity situation in a spherical thing where gravity is low at the center of the star and rises as the bubble rises out of the star. It accelerates from that, whereas we have good old, laboratory gravity. And the cylindrical shape is important because the viscosity is high enough that it does feel the shape of the container. So that's important. I never saw any pinch-offs, but that might just be that the star is too small for this thing to pinch off before it hits the surface or becomes turbulent or something. Whereas I can produce multiple pinch-offs up to 5 or 6. You have this complicated business of deflagration turning to detonation. Happily, we have no detonation in the experiment, okay? Nothing detonates. It's barely deflagrating, never mind detonating, so don't worry about detonation. All the simulations I've seen use T times 1 minus T kinetics. In other words, they use this nonlinearity for the temperature here. And that's kind of a standard simple flame model, whereas we're obliged to use cubic kinetics, and that has effects. That has the front depth effect, for example. The minimum size of the flame ball, I believe, comes from the fact that we have this cubic, whereas that doesn't happen, at least in Vladimir Ova's version. Some people use codes that have a kind of arbitrary power on the T here, and those are kind of different kinds of flame models, but they're all models of flame. So there may be other types of flame models out there, but the simplest one is just T times 1 minus T. Most of what we know, or what you know, which I don't know, about what goes on during the explosion of a supernova is done from large-scale computations, whereas almost everything I know is known from the experiment, and the computation that I've mentioned you so far captures it a little bit, but not really. Okay.
Did I, just to put it into context, suppose that there was a column 3, which was similarities and differences with respect to what people do in weapons labs around the world.
Right.
Because presumably they actually can go through some of those issues on the wild type
Yeah,
side.
I suppose.
And presumably they have tried to understand them because they get a lot of
Yeah.
and that's sort of what they do for a living.
Yeah, I assume that people who study real detonating explosives have codes and they study these things.
But
I don't know if
some of
any
it would be classified, but not all. I mean, you know,
No.
Flash was created in order to be able to simulate, I don't think I was used to that, to simulate the viability of the nuclear stockpile of the United
Right,
States
sure.
that we're talking about the money from.
Yeah. So-called scientific stockpile stewardship or whatever.
Yeah.
Yeah.
So in other words, there must, and somebody who's behind a proverbial fence probably knows a lot more than you'd be able to get in the local literature. But it'd be interesting just to see how that's related.
Yeah. Well, the IV arsenic acid experiment has been studied by people who do, you know, explosions and stuff like that. So there is some, it is used as a model flame front. We didn't invent that idea. Mostly what we invented was the idea of looking at a mushroom cloud in this. No one's done that before. But they've looked at it in slots and tubes and in geometries and argued that it's similar to you know, what you should get for an explosion.
But the work that you've done doesn't really map. I mean, you showed, you know, the political picture. But this work, because of the viscosity aspects, doesn't really map into the proverbial mushroom cloud.
No, that would be more like the supernova with a much lower, effectively lower.
Just because of the pressure gradient.
Yeah, and you know, the equivalent dimensionless numbers are many orders of magnitude. Let me just come to my my inconclusive conclusion. Okay, my inconclusive conclusion is: can we bring these two things together in the computer? It's extremely daunting to simulate the actual situation in a supernova explosion, and you're obliged to make computationally necessary simplifications, like you can't treat the Prandtl number of 10 to the minus 11 or what it really is, so you make it 0.1 or something like that. What I'm saying is, let's just, you know, simulate this simple thing. You guys should take your favorite supernova code and rip out all the really interesting stuff and dumb it down to the point where you can simulate my experiment. And I would claim that maybe by doing that process, we can learn something in the computer which we can transfer to the actual situation. So I finish with a challenge, okay? Take your supernova code and get me 5 heads to separate at the right time. I have data, I have everything, I can take absolutely everything you want to know, and if your simulation can produce 5 heads that break off in the right way at the right time, then that's a pretty severe test, at least of the dumbed down version of the code. And I gather that code validation is a serious issue, and so I'm offering my services by way of this experiment as a way of coming up with something that you could use to validate the code. It would be interesting for everybody, I think. Even though it's not a real supernova, it's at least similar enough to your code to be worth having to go at it with the code. Thanks very much for your attention.
So a comment on this last point.
Yeah.
So, I mean, I think the hydro parts of most of the supernova codes are fairly well understood. Most people believe that they work.
One hopes, yes.
Yeah. Now, the real challenge actually in these sort of decoration experiments on supernova codes is that there are a large range of scales, right? Between the flame width scale and the size of the star. And supernova codes, when you apply that experiment, are actually extremely distant. Right?
Okay.
And so it's the sub-physics which is actually not very well understood. Right? It's like basically, like for instance, like you showed that your flame head broke away and accelerated.
Yeah.
Right? So that's been one expectation of basically all these supernova models for a year, right?
But it doesn't.
Oh, but it does accelerate, right?
Okay.
The problem is that it's not clear.
Good job.
Wasn't a job, right? But that's because I think you put a really big flame ball in there.
Oh, okay.
Right, started with a bit. So,
All right.
right. But the really interesting issue actually in that case is that what's happening at the very, very small scales? Does everything get consumed, right? Or does or there are remaining amount of mixture of stuff which is not consumed? And I'm sure that this experiment can actually answer that question, right? Maybe because that your diffusivity is actually quite high in your experiment compared to your
Well, there's certainly no like small scale turbulence going on at reaction front really is, as I described,
Right.
really small.
Yeah.
But it's not, billions of orders of magnitude smaller. It's like, on the scale of 10 or 50 or 100 microns compared to 10 centimeters. So that's a dynamic range you might be able to simulate directly without having to make any assumptions.
Yeah. So.
But that doesn't mean that there's below that, there's some kind of subgrid physics going on. I don't think there is.
Or you can also turn that around, right? You can then simulate it at a level where you don't resolve the flame and check whether it actually works.
Yeah, you could do that. But the point is that the experiment is viscous enough, slow enough, and the fronts are thick enough that you ought to be able to, if you wanted to, just do everything correctly. In other words, simulate the experiment as it really is without any assumptions. And then, of course, you can back off on those assumptions.
So let's suppose you do another different experiment where, let's say you turn up you turn down the diffusivity of the concentration of the hydrogen ions so much that they don't really basically stay in place, right? So everything's driven just because of
Sadly, one does not have a knob on it. The only real knob you have is the viscosity. You could do, if you were willing to fund me, I could do an experiment in an enormous volume using water instead of very viscous stuff, and you would get real, honest-to-God, turbulent, plumes there. But then you would have the problem of measuring anything about them and disposing of thousands of gallons of toxic arsenic acid pollution. But at least it's a possible experiment, right? Just like if you want to do, moisture-driven convection, you can build an enormous can and heat the hell out of it, and you get real honest-to-God turbulence in the laboratory scale. But this isn't an easy experiment to do. It's at least physically possible, however.
Questions, comments?
It seems like in the parameter regime that you're in, of this stuff, there should be analytical things that could be looked at as far as.
For the Flameball, and at the very, very earliest stages, yeah, there are. That's what Vladimirova's paper is about, basically, scaling solutions of the initial, sort of asymptotically big small
For
state.
Schmidt number 9,000 marks over infinity.
Yeah, it is.
And so the drop in
Yeah. There is
by the temperature equation because there are groups.
Yeah, there are.
You can look at similarity solution.
Yeah, there are those things, and there are those things for ordinary thermal plumes. People have done a lot of those kind of things. The chemistry tends to screw that up, though. It's hard to see how to build the chemistry into it.
You have your equation down there, right?
Yeah, we have the equation.
Start there.
Nonlinear, and as far as I know, all the analytics apply to thermal plumes with point sources of heat and things like that. They're not reactive. But yeah, go ahead, do the theory.
Any more questions or comments?
Well, I just wonder how complicated it is inside of the star that starts its propagation. Because when you're pointing to uncertain and wild, you're actually pointing to the supernova remnant.
Yes.
Which is really complicated, obviously. But what's it really like when it starts?
Well,
Is it simple? Yeah.
this is what it looks like, as far as I know. Well, if I pause the movie, right, here, if I pause the movie in the first few seconds here, then it's quite simple looking.
Yeah.
So to add to your comment, so the thing is, the movie that they show up there has completely incorrect initial conditions.
Well, it has a
So-
sphere.
Well, no, it's true. That's right. Okay, but so the central temperature of that plume is something like maybe 10 to the 9, maybe like 10 to the 9 degrees Kelvin. But all the material around it is roughly 10 to the 5, 10 to 6 Kelvin. Okay, that's a completely artificial initial condition. Right, and the only reason why it's thought to be that is that it's thought that that temperature does not matter. the topic thing was. And this has been done more or less for the last 30 years, trying to do the same similar law and going basically to higher and higher resolution.
No, but the other key ingredient is surely the choice of the offset. It's an off-center detonation, it means that that's defining the wire key.
Yeah, so
that's obviously the
right.
as well.
So one can make some arguments as to basically how far offset and how big of propagation of the initial flame that can be. Basically. Just by looking at basically if the interior is convective and you take one convective plume, plow to the center, have some nuclear reaction rates go through it, you can basically argue, well, like when it actually finally goes, it's like maybe 100 particles or 200 particles. And so one can make an argument as to how offset that is.
And the assumption here, but is it considered to be the right assumption that once you hit ignition, it's a rare event, so that's where the big fluctuations are, so you aren't going to get multiple centers.
Okay, so in the flash bulb, right, what they like to do is they put one big guy in there and then let it run away. Okay. Now the other group, which is the German group, Wolfgang Hillebrand, they used to put multiple events, so it would basically definitely a causal, right? So all at once you have like roughly about 1,000 points that would all run away at once, right? And when that didn't work for them, that's when they basically gave up the large property on their initial ideas of how supernova running happened.
So you mean now people believe it's a single event?
No, this is where the deprivation detonation comes from. It used to be thought that it's all deprivation.
Oh.
But the thing is that deprivation, you burn one thing, if it goes out, you see it burn like maybe like a few percent of the star, maybe 10% of the star, and it's gone, right? Okay. So the thing is that they lit it at 1,000 points, hoping to burn all the stars, right? But when that didn't work, it's like, okay, yeah. So that's the problem is that never didn't quite work.
So this argument that it detonates
Yes.
is so full is a kind of Hail Mary.
So that's a bit of a Hail Mary kind of task that we're trying to make it work, right? Because in fact, right now, you have roughly about 10% of star burn. 90% of the star will be destroyed when the detonation happens. That's really what's
responsible. You need that to explain the operation.
Yes, you need that, yes. You need 90% of the star blowing up.
Well, I can't help you. I would say that there should be a meeting of the mind between the people who work on this kind of low Reynolds number precision fluid mechanics and the people who have these monstrous codes that can do this high level stuff. And it would be interesting just make the two mesh together, as I was saying at the end here. Because there's quite a lot of people who are not in possession of nice codes to simulate even relatively gentle things like this experiment. And you have those codes. So I would like you to run the appropriate regime. It's harmless. It can't go wrong. If it does go wrong, then you're in big trouble. Anyway, thank you very much. It's been very interesting. And I hope we'll talk some more.
Yeah. So let's thank the speaker once again.